Hi, and welcome to the second part of the Pendulum Motion series. I had to cut the first part short because the screen recorder that I'm using, only allows me to film 15 minutes at a time. So that's why I'm making uh, the second part to the Pendulum Motion video. Okay, so just picking up where we left off, we have the pendulum here. And we agreed that there's a force of mg I hat on it, there's a force of negative t sine theta j hat on it, and there's a force of negative t cosine theta I hat on the pendulum. Uh, the sum of all these force vectors is just the force vector that acts on the pendulum. And I just want to remind you that theta is not a constant, it's a function of time. Okay, so let's see what the force vector that acts on the pendulum actually is. So adding all these force vectors together, we get mg minus t cosine theta I hat plus negative t sine theta j hat. So that's our force vector that acts on the pendulum, total force vector. But we know that's equal to mass times our acceleration vector. Okay, that's just Newton's second law. So our acceleration vector that acts on our pendulum is g minus t cosine theta over the mass of the pendulum I hat plus negative t sine theta divided by the mass into j hat. But we've also worked out the acceleration vector here, all right? Just highlighted in green here. So these acceleration vectors are the same thing. In which case, what we can do is we can equate the x component or the component of acceleration right next to the I hat vector. So we can equate. I'll use another color. We can equate this part here, and we can also equate. I'll use another color. We can also equate this part here and this part here. So this part, the screen's really messy. So I'm just going to transport these equations to another screen. Alright, so all I've done is I've equated the I components of both acceleration vectors and j components of both acceleration vectors. So equation 1 is equating I components, I hat components, I should say. And equation 2 is equating j hat components. Alright, so we have two equations, and we're going to solve both equations and derive an important relationship between the angular displacement and the length of the pendulum and the gravitational field. So first of all, we notice that there's a negative t divided by m, so negative tension divided by m in both equations 1 and 2. So that's a start. We're gonna try working from there. So negative t over m from equation 2 we see is just L theta double dot cosine theta minus L theta dot squared sine theta divided by sine theta. So we know this from equation 2, and we're going to sub in this result directly into equation 1. So let's do that. We have negative L theta double dot sine theta minus L theta dot squared cosine theta equals G plus L theta double dot cosine theta minus L theta dot squared sine theta. I apologize, this is taking a really long time, so if you want to, please skip ahead to after I've finished writing all this stuff down. Now, we have a sine theta in the denominator of this expression on the right side of our equality. So we're going to get rid of that and by multiplying both sides of the equation by sine of theta. So let's do that. We get, I'm just going to expand it all out on the left, otherwise I fear it's going to take way too long. So I'm multiplying both sides of this equation by sine theta. Alright, let's see what happens to the left side of the equation. We get negative L theta double dot sine squared theta minus L theta dot squared sine theta cosine theta. And we're multiplying both sides of the equation by sine theta, so we get a G sine theta here, and over here, well, the sine theta just cancels, and we're left with cosine theta into L theta double dot cosine theta minus L into theta dot squared sine theta. So let's expand all of that out as well. We get L theta double dot cosine squared theta minus L theta dot squared sine theta cosine theta. Now, we have a negative L theta dot squared sine theta cosine theta common on both sides of the equation. So we can just cross those out, cancel them, and we're now left with an equation that looks a lot nicer. Let's completely just cancel these parts. Let's move this this negative L theta double dot sine squared theta to the right side of the equation. All right, so we get G sine theta plus L theta double dot cosine squared theta plus L theta double dot sine squared theta equals 0. So all I've done is I've moved this negative L theta double dot sine squared theta to the right hand side of the equation, and I've got this. Now, the first thing I notice here is I can factor out an L theta double dot, and I'll actually just get L theta double dot, because we all know that sine squared theta plus cosine squared theta for any theta is simply 1. So let's do that. So we have G sine theta plus L theta double dot into sine squared theta plus cosine squared theta equals 1. Oh, sorry, equals 0. Okay, I'm just going to delete some of the stuff I've written above. It's getting a bit messy. And I'm going to rewrite this equation on top. Okay, so we have G sine theta plus L theta double dot sine squared theta plus cosine squared theta equals 0. I'll just get rid of this stuff on the bottom as well. Okay, now we know that sine squared theta plus cosine squared theta, well that's just 1. So we can further rewrite this as G sine theta plus L theta double dot equals 0. And if we want, we can even divide everything by L, the length of the pendulum. Well, we know the length of the pendulum is not 0, so we can divide everything by L, and we actually get theta double dot plus G over L sine theta equals 0. And remember, theta double dot is just the second derivative of theta of t. Remember, theta is a function of t. Of t. Okay, theta is a function of t. It's not just a constant angle. Okay, so we have this really nice looking equation. Now, how do we go from here to the pendulum motion equation for small angles that you're taught in physics class? So, for small angles, it's a known fact that sine theta is approximately theta when theta is small. So, and by the way, we always work in radians when we deal with small angles. If you want to know the reason for this, it's essentially because when theta, the limit of theta approaches 0, of sine of theta divided by theta equals 1. Right? That's essentially the reason why for small angles, for theta very close to 0 radians, sine theta over theta, this quotient is 1. Okay, or very, very close to 1. So, given theta is a small angle, all right, so given theta is a small angle, I'm not actually going to prove this result in this video, but if you like, you can take a small angle in radians, take something like 0.005 radians, and put it in your calculator, work out sine of 0.005 radians, and you'll get a result that's pretty close to 0.005 radians. Alright, so we'll use this result and we'll see what this equation we've derived turns into. So when sine theta is approximately theta, well, when theta is a small angle, the equation just changes to theta double dot plus G over L theta, because sine theta is approximately theta, is equal to 0. Now this is actually called a second order differential equation if you're interested. I'm not going to be properly solving the second order differential equation in this video, but I will be verifying a solution to the second order differential equation with certain conditions. So I'll explain what I mean by that in just a sec. So given this equation, suppose I say, well, I know what a solution is. I know that theta could be theta max cosine root G over L t. And remember, theta is our angular displacement function. So if this is truly a solution, then it should satisfy this equation. So let's check. Well, theta double dot, second derivative of theta with respect to t, is simply, well, I'll do this. I'll skip a couple steps here, but it is actually negative G over L theta max, negative G over L theta max cosine root G over L t. Alright? And we know that G over L times theta, well, that's just G over L theta max cosine root G over L t. So if we sum these two together, we do indeed get 0, and so this is a solution to the equation we've derived above. Now we know that theta t is equal to theta max cosine root G over L t. And we know this is a solution. So how long does it take for the pendulum to go here and back? Well, when the pendulum crosses past the equilibrium point over here, theta max is negative, and then it goes back, and it's at theta max again. So one full time period is the time when theta over t is equal to theta max, but t is not 0, because when t is 0, theta of t is theta max. You can verify that here. Also at t equals 0, we note that the angular speed is equal to 0, which basically means we're suspending the pendulum at t equals 0, which makes sense. So how long is one full time period? Well, I've solved the equation for you over here. Take a look at it. There we go. The pendulum equation is derived. Thanks for watching.